Hey guys, welcome back to my channel. I've been doing a bit of cloud pen testing, learning the rudimentaries of Kubernetes, and I have this wonderful room on TryHackMe that is very simple, at the same time, very not simple. Okay, let's get started. I'm going to start with how I got to this room. You come to learn. From learn, you're going to come to search. Then for this one is Kubernetes. Enter. Because I'm on a free subscription, I'm going to come to subscription type and go to free only. Then I'm coming to Kubernetes best security practices. Excuse me. I just completed this room like some minutes ago. I'm going to reset progress, and I would love to teach it. If you are interested, I am hoping that you are here because you are interested. Yeah. Thank you so much. In this room is basically for the best Kubernetes security practices at a cluster level. For you to be here, that means you have like an introductory knowledge of Kubernetes, containerization, and all that. Yeah. So this room is for all those aspiring DevSecOps engineers and those Kubernetes enthusiasts who have taken the time to learn the basics of the tool. So what this means is that you already know the tool and you know how it works and all that. But now you've built a cluster and you're thinking of how to keep it secure. And that's why you're here. So we have many different security considerations that must be made at different layers, and this can be overwhelming for those looking to up about DevSecOps Express. So even for those that are already there, it can be a bit overwhelming. So what this room aims to do is to collect some of the key best Kubernetes security practices to make your journey much smoother. All about. I'm having fun. So we have prerequisites for this room. You need to do introduction to Kubernetes. You need to do the cluster admin room, then the introduction to containerization, introduction to Docker, then the container admin rooms. So these are all the rooms you need to be familiar with. Some of them are on premium. However, because I took my own introductory courses from the Linux Foundation, it's pretty much similar. This just has more hands-on. The learning objectives for this room includes understanding the importance of implementing best security practices in Kubernetes, understand service accounts in Kubernetes, their function, and best security practices surrounding them. Understand how to independently define roles and role bindings to implement RBAC on a cluster and why this is needed. And you also have to understand API requests in Kubernetes. We are going to click on complete. We are going to move to the next task. Service account. What is a Kubernetes service account? One of the most important security practices in Kubernetes is the efficient and secure implementation of access control. Service accounts are a part of this access control, and you need to understand how to implement them. They were briefly touched in the introduction room, but now we are going to take a deeper look at what they are and how they are used in Kubernetes. In code, service account is a general term that you may be familiar with if you use other cloud technologies. In this task, we will define a service account in the context of Kubernetes, that is, a service account object. Service accounts can be thought of as digital identities or non-human accounts. And in Kubernetes, this identity is used in a security context to associate an identity with a specific process. In other words, Kubernetes system components, application pods, or other entities, but both inside and outside of the cluster, can use service account credentials to identify as the service account. So what this means from a security perspective is that API authentication can take place, or just as we've mentioned, identity and access control can be implemented using these service accounts. You may now wonder what's the difference between service accounts and users. So now we are going to be emphasizing on the non-human account aspect of a service account, and we are going to clear up any confusion regarding human users being authenticated or authorized into a cluster. So here is some information regarding service accounts and users. Service accounts are managed by the Kubernetes, while the users are managed outside of Kubernetes. Service accounts are created by the API. For the users, there is no user in quotes Kubernetes objects. Don't forget that in Kubernetes, the context of service accounts here is as objects, service accounts object. Service accounts have associated credentials which are stored as secrets. While in users cannot be created by API in the real sense. So we don't have secrets. Essentially, user access is usually handled using some kind of account management solution. Kubernetes does have one built in, but this is generally integrated with another user management system, such as LDAP or AD. AD means Active Directory, and LDAP is Lightweight Directory Access Protocol. That's just like a protocol. So non-human access to the cluster and its resources is managed by Kubernetes service accounts. So let's tell you more. Service accounts are characterized by three attributes. They are lightweight, they are namespace, and they are portable. What do we mean by being lightweight? They are lightweight because they allow you to create an account associated with a specific stack or process in your Kubernetes cluster. So this saves many of the headaches that come with using a user account to run processes. In that way, we have special systems and business logic tied to databases involved in user account creation. So because we are using the service account, it makes it easier to define more granular task specific permissions following the principle of least privilege. Two, they are namespace. In Kubernetes, service accounts are a namespace resource, meaning service account names need only be unique within the namespace they are associated with. Every namespace upon creation gets a default service account associated with it, aptly named default. So let's assume you don't manually define a service account in the pod or deployment definition. In that case, this default encode service account that is in the namespace that the pod is being created in will be assigned to it. So let's say you do not manually define your service account in your deployment. So there'll be a default one that will be attached to it, right? So, and the service account credentials, which is a token, will be mounted to it as a secret. That's like base 64 encoded. Now, you have to note that the default service account that is created on your behalf is going to have a few permissions by default. So if you need to grant a task more permission, you need to create a service account specific for that. Thirdly, they are portable. Because service accounts are lightweight and only need to be unique at a namespace level, they can be bundled together for use in other namespaces or projects, making them portable. These attributes lend themselves to several use cases. As a DevSecOps engineer, your service account sense should tingle when dealing with those. Here are some examples. Number one, a task or process running in a pod needs to communicate with the API to retrieve secret or sensitive information. A service account could be used here to grant read-only access to these secrets. You have a pod running in a namespace, let's say example namespace or a namespace. Each process involves ensuring all pods are running in B namespace. A service account can be used here, because A is in relationship with B. A service account can be used here with a combination of a role-based access control to ensure that this pod has sufficient permission to list pods in B namespace. So what this means is that if we have a pod that is running in A namespace and we need it, and its process involves that all the pods are running in B namespace. So we can use a service account here with a combination of RBAC to ensure that it has the sufficient permission that it needs. And thirdly, service accounts can be used to authenticate external services. For example, imagine you have a CI/CD pipeline and a stage in this pipeline involves authentication to your Kubernetes cluster. Making sense? Thank you. Creation and configuration of service accounts. Service accounts are very easy to define using kubectl. You can create a service account on your cluster using the following command. Also note that a service account can be abbreviated as SA. So in this command, we have kubectl create service account. This is the name of the service account. That's example name. We can also say A or Alice, then the namespace, then Alice namespace, something like that. Very direct. If you wanted this service account to be associated with a specific pod, you would define that in the pod or deployment configuration YAML, like so. So that's like the file. We have the API version, we have the kind, which is pod, and the metadata. If you are using a pod or Alice pod, the name is going to be Alice pod, and the namespace is going to be Alice namespace. And for the specification, we have the service account name, which is Alice SA, and we have the containers associated with it. That's Alice container. We have the image from Nginx latest, and we have the port, which is container port 80. So this is just like an example of what is going to be in the YAML file if we are actually trying to define pod or deployment configuration. So you can create the account, then you also create the file. What are the credentials associated with a service account stored as? That's going to be the secrets. Kubernetes service accounts are lightweight, namespace, and they are also portable. Easy peasy lemon squeezy. We move on to role-based access control. Now, why role-based access control? Part of best security practices is preparing for worst-case scenarios. Now, you have securely built your Kubernetes cluster. You followed best practices to add in that cluster, but you need to be prepared for scenarios where attackers gain access to the cluster. More specifically, the attacker will gain access to either a pod or application or a user. In other words, they are authenticated into the cluster. Both will have associated permission and be authorized to perform certain actions. It is then the job of a DevSecOps engineer to ensure that these permissions are configured with least privilege in mind. In summary, what we are trying to say is that you've done everything right, but you need to be prepared for when something goes wrong, because there is always an attacker somewhere. So that eventually, if they get access to your pods or the application or the user, what are the things that are in place to prevent them from moving further, from escalating their privileges? For example, a pod which checks the running status in the X namespace should only have the required permissions to perform that action and no other permission. So this way, if an attacker were to gain access to this resource, they would only be able to perform authorized actions, which in this case would give them little access. We can implement this using role-based access controls. So for this, we can see that can pod admin delete resource pod deleted. So you can see can pod checker delete resource pod. You can see it was banned out. Pod checker cannot delete resource pod. This is just like an example. To begin with, let's define what 4 different Kubernetes objects that can be defined when implementing role-based access control. We have 4 different Kubernetes objects definition for RBAC. We have the role, we have the role binding, we have the cluster role, and the cluster role binding. What can this role do, and to what resources? Permissions are additive, meaning that there are no deny permissions. So you think of this as allowing list for API access. You provide a verb that is what can this role do, e.g., get, delete, list, and all that. And the resource. So what can this role do to this resource, e.g., pods or secrets? That's our resource. Note that sub-resources can also be defined there using a slash after the resource name. For example, pod/log. This will be visualized with a configuration example soon. So roles are namespaces, meaning they can allow actions within a given namespace, not the entire cluster. Role binding. The role binding object does what it says on the tin. That is, it binds a role that has been defined above in the role to a service account or a user. As roles are namespaced, the role mentioned in the role binding configuration YAML file will need to exist in the same namespace as the role binding. That means they follow along, they're in tandem. What role binding does is just to attach the role to the service account or the user, like that. We move on to cluster role. You should be able to get what cluster role means now. A cluster role is functionally the same as a role, except that roles are granted on a cluster level. Cluster role. This would be used if access is needed to cluster level resources like nodes or resources across multiple namespaces. Again, only if this is needed, with least privilege in mind. Cluster role binding. A cluster role binding is functionally the same as a role binding, except it binds a cluster role to a service account or user. Just the way role binding is going to bind a role to a service account or user, a cluster role binding is going to bind a cluster role to a service account or user. Let's have the role-based access controls in context. Now that we've established different kinds of RBAC objects, let's give some more context as to where this would be used. As mentioned, roles can be bound to either service accounts or users. Service accounts will be used if we are granting authorization to an application. For example, an application running in a pod within the cluster or a third-party external service like Istio. Meanwhile, users will be used if we are granting authorization to, well, you guessed it, users. Now let's look at RBAC in the context of both of these. We have the service account and the user. In the context of role binding for service accounts, a role and role binding will be used to allow an application or a pod to perform a certain action on a namespace resource. For example, excuse me, allow a pod to get the running pods in a namespace. The pod will then have this service account assigned to it. For the cluster role or cluster role binding, this is the same as the role or role binding, but for performing actions on a cluster level resource, like a node. For users, we imagine that we have user Bob who has been tasked with monitoring pods in the dev namespace to ensure a deployment is in a working order and can be deployed in staging. For this, the user should be granted permission to get pods in the dev namespace. Using a role would be preferable in this case since we are defining a namespace resource and the user should only be able to access what it needs to, not pods in all namespaces. For the cluster role or cluster role binding, let's imagine that we have another user called Alice. Alice is a cluster admin and needs permission to create multiple resource types across all namespaces to set up the cluster. For this to be authorized, a cluster role would need to be defined and bound to Alice's user with a cluster role binding, since the authorization required is at a cluster level. So depending on the authorization that is required, we choose between role binding, or cluster role binding. How do we define RBAC? We are going to consider the example we have earlier. So let's say we have a pod that is supposed to check the running status of pods in the example namespace. The pod identifies as example service account. Then this is what the definition YAML file will look like. We have the kind, it's a pod. Then we have the metadata. So this is up checker, and the namespace is example namespace. This is what the pod definition file, right? This is the service account name, and these are the containers. So we have the just one. We have kubectl, and we have the image here. So we want to ensure that this pod has only the permissions required to perform this object. So to do this, we'll first define a role looking something like this. So in this case, we are defining a role. That's why we have role here. And we have the name of the role, which is upchecker role. And we have the namespace. Don't forget, it's still the same namespace from the pod definition. And we have the roles. The rules here: get, list, and watch. Those are the actions you can perform. And the resources you can perform it on is just the pods. Now, we already have our role that allows Bob to get, list, and watch on pods in the example namespace. Now, we need to bind this role to a user or a service account. Since our pod use the service account, example service account, we want to bind the service account to the upchecker role. What this means is that we have our pod definition, and is using a service account name called example service account. We have our role definition. We want to bind this role to this example service account. That way, this example service account can perform these actions on the pod, right? So we are going to define a role binding. This is how the role binding is supposed to go. We have the kind, which is role binding, and we have the name, which is upchecker role binding. Don't forget, the namespace still remains consistent. Then we have the subjects. Now, that's how you'll be able to see the differences. We have the subjects, which tell us the kind, the name, and the namespace again. That's the service account. And the name of it is the example service account. And we also have the namespace, which is consistent. Then we are referencing the role, which is role, upchecker role, and the API group. Here, we tell Kubernetes the subject. In this case, we have just one subject to which we want to bind this role, that is the service account, and what role we would like to bind the subject to, that is the upchecker role. Remember, we can apply each configuration YAML using the following commands: kubectl apply, then f, then file name dot YAML. I hope that is clear. So defining a cluster role or cluster binding is almost identical, except that there is no need to define a namespace, and the kind will be changed to cluster role / cluster binding. Let's answer the questions below. We have defined a role. What should you now define to associate that role with an identity? That's going to be role binding. You now want to define permissions at a cluster level. What do you define? That's cluster role, because it's a cluster level definition. In which field under roles would you define the actions that can be performed on a resource? So that's the verbs part. We come here, you're going to see that we have verbs, and that's where we define the permissions for the resource. In which field under rules would you define to what those actions to be applied? That's going to be resources. We apply rules to resources, right? Should we stop now or should we go on? Let's see how much we have in the next room so I don't bore you. Okay, I think we can still take this. API requests in Kubernetes. So if you are going to secure anything and follow best practices, it is fundamental that you understand how exactly it is being accessed. Between this room and the prerequisite, you have now accrued enough knowledge to understand how a Kubernetes cluster is accessed. This starts with collect the knowledge covered so far and use it to explain methods of accessing a Kubernetes cluster and the API requests involved. We have our cluster, we have the access method there, and we have the API. Accessing the Kubernetes API. Accessing the Kubernetes cluster is done through the use of the Kubernetes API. This is our communication channel to the cluster, and there are different methods of accessing the Kubernetes API itself. We have the kubectl, we have the proxy, we have the authentication token, and we have the programmatic way. One, kubectl, we've covered this before, and this is the Kubernetes command line tool. When accessing a cluster, you need to know two things: the cluster location and the credentials. When configured, kubectl handles the locating and authenticating to the API server, making it easy to perform actions on the cluster using various kubectl commands. This is the most common method of accessing a Kubernetes cluster. However, if you wish to directly access the cluster yourself, that is using curl or wget or a browser, there are a couple of ways to do this. The second method is proxy. kubectl can be run in proxy mode using the kubectl proxy command. This command is going to start a proxy server on port 8080 that will now forward requests to the Kubernetes API server. This is the recommended method for directly accessing the Kubernetes API because it uses the stored API server location and verifies the identity of the API server using a self-signed certificate, meaning that a man-in-the-middle attack is not possible. I think you should be able to understand this lingo if you actually went through networking proper. The third method is authentication token. This method accesses the Kubernetes API directly by providing the HTTP client with the cluster location and credentials. For this reason, it is not recommended as it will be vulnerable to a man-in-the-middle attack. Programmatic. Kubernetes supports programmatic access to the API using client libraries. It officially supports client libraries such as Python, Java, JavaScript, Go, and some community-supported libraries, although these do not have official Kubernetes support. So we can use the kubectl, that's the command line tool for Kubernetes. We can run proxy. We can run authentication token, which is not advised, it is not recommended, and we can also use programmatic access using client libraries. Now the API request stages. Now we know how to connect, how to access the Kubernetes API or cluster, right? So from this point, the conversation turns to how we control access to this cluster. You'll be pleased to know that much of what you've learned thus far has been methods of controlling access to a cluster. Now, let's contextualize them by looking at the Kubernetes API request stages. When you communicate with the Kubernetes API, you'll be asking to do something, whether that should be getting some logs, creating a pod, or deleting a service. When you perform one of these actions, you'll be sending a request to the API. This request will go through multiple stages before being actioned. Now, let's take a look at what those stages are. 1. Authentication. 2. Authorization. 3. Admission controllers. Authentication means that you are who you say you are. Authenticating an API request can be done in multiple ways. These include methods that have been covered in a previous room, such as setting up client certificate authentication or using API bearer tokens. Authentication can also be done using other authentication plugins, such as the authenticating proxy or HTTP basic authentication. Another authentication method would be service account tokens, which are used to authenticate a Kubernetes service account. Multiple authentication methods can be used, and it is often the case that at least two would be used. A request passes this stage only when it has the right attributes needed to confirm the requestee identity. Authorization, second stage. This means that you have the permission to do what you are trying to do. Once the requester's identity has been authenticated, it needs to be determined if this user or service account is allowed to make this request. That is, can it have access to this resource? For example, does user A have sufficient permissions to delete pod B? The request needs to be authorized, and Kubernetes has four authorization modes. One commonly used and the most important for our current context is the RBAC, the role-based access control. There are three other authorization modes, and they are the node authorization, the attribute-based access control, and the webhook. For node authorization, you can remember that a Kubernetes cluster has a kubelet process running in each node. So this process communicates with the API, and this authorization method is used to authorize requests made by kubelet processes. This is not intended for user authorization. Attribute-based access control. This is similar to RBAC, the role-based access control, but instead of granting authorization based on roles, it grants it based on attributes. Yeah, good. Now, these attributes include user attributes such as the name and position, resource attributes such as the creation date and the resource owner, or environmental attributes such as the time and location from which the resource is being accessed. ABAC allows for a very granular level of access control. For example, you could allow a user to access a resource from one location, that is an office, but not another location, such as their home. However, implementing this for a growing user base can quickly become complex, and the maintenance of ABAC policies can become difficult. This is often cited as a reason why RBAC is favored over ABAC for organizations. That is, its implementation simplicity. The third one, we have webhook. This is another authorization method for delegating the authorization to an external HTTP service known as a webhook. A webhook allows a user or organization to define custom logic for authorization and have API requests authorized using this logic. This is useful for organizations with more complex authorization requirements or ones that want to defer to an external service like LDAP or Active Directory to make their authorization decisions. The webhook will then send back a response based on the outcome. Now, using one of the methods above, a request is checked to see if the authenticated user is authorized to access the resources or perform the action requested. Now, before the request is accepted, there is one more stage. That's the admission controllers, which means that does this request pass all checks? After a request has been authenticated and authorized, the next API request stage is admission controllers. Admission controllers are checks done against an API request. They can be validating or mutating. Validating in the sense that is this action permitted? Does it breach a check? Or mutating in the sense that in a request to create a pod or the pod's name might need to be changed to match a custom naming convention. So what this means is that the action you are trying to carry out, does it pass? As well as built-in admission controllers, you may remember that it is possible to define custom checks. So these admission controllers are triggered after the authentication and authorization stages And only after all admission controllers check have been passed will this request persist. Moving on. We have followed an API request through all of its stages. When asked how to restrict access to a Kubernetes cluster, you should now be able to elaborate more than just adding your cluster and discuss how a cluster is accessed, how access can be restricted at each stage, and how your admission controllers can check either by validating or mutating. Great work. Your DevSecOps skills are growing with every task. We have our questions here. Which cluster access method will be vulnerable to a man-in-the-middle attack? That's going to be the auth token, the authorization token access method as it was mentioned. API request stage would RBAC be involved in? That's the authorization. In which API request stage would we find the words mutating and validating? That's the last one. Admission controllers. In which API request stage would a service account token be used to verify a service account? That should be the authentication. We are using a token. Let's see. To be authentication. Yeah, service account tokens. With this, we are going to pause for now and we are going to continue with the remainder of the room in the other video. Thank you very much for listening. If you have any question you'd like to ask, feel free to put it in the comment section and I'll be glad to help. Bye.